has now come down to this level based on the end of this huge glacial age. And when we take a look here, the last 3 billion years of Mars history has been a glacial epoch. But before that, we have these huge outflow channels, and we have northern oceans in the northern lowlands. And before that, we have valley networks that look like Mars was actually warm and wet. So Mars history is just incredibly informative. It's the history of water on the planet, on a moon and Mercury-like planet with an atmosphere and with water and polar caps. And we can see the change from a much warmer and wetter surface of Mars up to what we see now, which is a hyper-arid, cold polar desert. How does that happen? Is the Earth headed in this direction? Is global cooling going to follow global warming? What's going on here? These are all perspectives we can study on Mars as well. Indeed, when we look back into this area here, one of my recent PhD graduates, Caleb Fassett, has mapped 210, actually every day he tells me it's gone up, so it's probably around 214 now, open basin lakes. This means we see a channel going in and a channel coming out. This implies that the thing was filled with water and coming in and then filling up and then flowing out the other side. 210 of these, each one of these features here. All of these other things are channels. This was a very different Mars than what we see today. There was liquid water on the surface, flowing across the surface, and of course, lots of opportunity for indeed the presence of life. Now, if we take a look at Mars then, it's Moon and Mercury with water and climate. That's pretty amazing from a comparative planetology point of view. Similar to the Moon and Mercury in many ways, tectonics, a one-plate planet. We don't see any sign of plate tectonics, but it's a significant record of early impact history, but it differs in very fundamental ways. We see differences in a whole host of things here, but one of the most important is this early warm and wet Mars is a likely habitat for the formation and evolution of life. A lot of people argue, why don't we see evidence for life in the earliest rocks on the Earth? And there's a lot of debate about that, but one possibility is, you know we get meteorites from Mars blasted off Mars now. There must have been many more coming then. One possibility is that actually life didn't start on the Earth till a meteorite from Mars dropped down in the ocean and seeded it. I mean, enough of this, search for life on Mars. Maybe we're looking at it in the mirror, for crying out loud. I mean, that's not proven by any stretch of the imagination, but stranger things have happened. So maybe we're all Martians. Maybe we originally came from Mars. Something to think about. We never would have thought about that without these kinds of data. What about Venus? Now, this is the most Earth-like planet in terms of its position in the solar system, its size and its density, so maybe this is the Rosetta Stone, if you will. Maybe we are actually looking at the Earth with a slight variation. Maybe this is the big lesson. As luck would have it, of course, it took us a while to figure this out because, in fact, it's hard to explore Venus for a variety of reasons. If we take a look at planetary history here and start with the present and work our way back, remember that when we took a look at the Earth, there was very little record on the surface of the planet left over from the early period of history. And most of the recent history is in the ocean basins, 60%, less than 200 million years. So when we start here, we have the ocean basins, we have continents, and it's very, very spotty back in here, almost nothing back in here. On the other hand, the Moon, Mercury, and Mars are Rosetta Stones for the early history. They've left the record from this time. We can study it. We can figure out impact craters are important. Maybe the Earth was a one-plate planet at the beginning. How did it get from point A to point B? Well, maybe Venus is the answer. We hoped that either it would be like the Earth with plate tectonics, or it would be like the Moon, Mercury, and Mars, in which case size wasn't as big a deal as we thought, or maybe it would be the transition between the two. Maybe it would be in here somewhere, and we'd be able to see something what looked like going from a one-plate planet to the present-day Earth. So this is really exciting, and it propelled a significant amount of Venus exploration by the Soviet Union and the U.S. Now here's an atmospheric scientist view of Venus. It's not an easy place to explore. Opaque clouds, in fact, okay, think about it from a spacecraft point of view. Opaque's one thing. Sulfuric acid, hydrochloric acid, other things, in the atmosphere are not real good for spacecraft, health. And so we have here all kinds of things going on in here. We find, in fact, H2SO4 concentrated at various levels in here. And, of course, what this reflects, because of the density of clouds, is the decreasing level of knowledge as you go down towards the surface. We have almost no information about what the lower 20 kilometers look like. You can see the lingo dying out as a function of depth in the atmosphere. Very sophisticated cloud decks and so on, haze zone, and then red murk. What can I tell you? And, of course, you can tell it's the atmosphere's people because look what they say about the geology. Surface mostly flat. That's me, you know, it's geology. It's not mostly flat, it's really interesting, and the combination of the two has, you know, really increased our understanding of this unusual planet. Now, the first thing you had to do was to get through this stuff, and the Soviet Union did that in spades, wonderfully and beautifully. They were able to launch a series of spacecraft to Venus that landed on the surface, starting with Venera 9, and send back images of the surface, make geochemical measurements. And I have to tell you, this is a remarkable engineering achievement. So interesting that I proposed this some later for one of the first Discovery missions to send this using U.S. instruments on these spacecraft back to Venus. Unfortunately, it fell, that's another whole story, but it fell askew, if you will, of international relations and economics in terms of launch vehicle industry and a few other things. It is a long story, which I won't tell here, but it's a beautiful, beautiful thing. Believe it or not, see these things here? Those are shock absorbers, just like you have on your truck out here. It's amazing. When this thing comes down, they're shock absorbers, and it's beautifully engineered, worked flawlessly. This is the surface of Venus. I mean, imagine that. This picture was taken decades ago by a very capable spacecraft. You can see the rocks and the geology, the base of the spacecraft, sampling, all sorts of things went on here. And indeed, this was the coin of the realm until Magellan in the early 1990s. And let me just pause here and go back to Tim Much. I told you that there were 3 people in this class who were told that there are no fundamental problems left in Earth stratigraphy. One of the others was Steve Saunders, who ultimately became the Magellan Project scientist. So he too was influenced by Tim, as I was, to reach out and not just sit and do uninteresting problems on the Earth. And of course, Steve was the project scientist for Magellan. This is Ellen Stofan. You may remember Andy Stofan. This is his daughter. She was one of my PhD students. She was a deputy project scientist right out of grad school. So thinking about my situation in Apollo, where I was able to go straight into a job like this, it's a beautiful place for opportunity. Ellen went right in as deputy project scientist and did a superb job. She's one of the foremost Venus scientists in the field today. Magellan was revolutionary. We got 97% of the surface, beautiful images. It was a volcanic planet, but more to the point, it was really enigmatic, okay? It turns out that the surface of Venus is young, and young as the Earth, but it has no plate tectonics. So what do you do with that? How can that be? When we took a look at the surface, it's completely resurfaced by volcanic activity, and when we look at that volcanic activity, it's essentially wiped out all the craters on the planet. Something must have happened late in Venus's history to cause the complete surface to be resurfaced, to be modified completely. That means to say, if you took the complete Earth's surface today, you'd have to remove it and add new surface in a very short period of time. Now, this is something that's just revolutionary. We've never seen this in a solar system. So we had, would the Venus be like the moon? Would it be like the Earth? Would it be like something in between? And as one of my colleagues, Tom McGetchin, told me years ago, don't forget D, which is none of the above. And that's exactly what Venus has turned out to be. So what we found out that, in fact, was that Venus was very young. If you take a look here, in fact, the number of craters on the surface is randomly distributed. Here is a plot somewhere in here of the distribution of craters on the surface of Venus. The other 5 are random distributions of points, just randomly generated by a random number generator. You can't tell the difference. That means that Venus underwent huge resurfacing in its relatively recent history, and that means that this is like something we never even thought about before. So could Earth do this thing as well? I mean, we're not used to this amount of geological change, complete overturning of the planet's surface in the last billion years. This is just not something that was on our radar screen at all. So we learned from Venus that, in fact, its age is here, but it doesn't have plate tectonics to produce the kind of configuration we see on the Earth. So we learned from this that planets can move around in terms of how they get rid of heat and how their surfaces are modified. So in fact, this is a big lesson for us, and we think about this from the point of view of how plate tectonics started. Because we don't have the early record, nobody knows how plate tectonics started, but it's how the Earth works. So one of the things that Venus is telling us is that this huge overturn of the surface earlier in the history of the Earth may be what started this on the Earth. That's big news. It's a new perspective and a fundamental perspective. Let's take a, as Scotty would say, Warp 7 tour through the rest of the solar system and think a little bit about comets in the asteroid belt. We have learned so much about comets. Look at this here. Could you ever imagine yourself looking at the nucleus of a comet? We've seen 3 of them at least. And of course, this place shows where the impact was.